In this video tutorial, we're going to look at two ALOS PalSAR acquisitions over a part of the Amazon rainforest in order to extract deforested areas. Each image includes two polarizations, horizontal transmit, horizontal receive, and horizontal transmit and vertical receive. First, we will compare the two polarizations to determine the deforested areas, and then we're going to compare the two images to extract the areas which were deforested in between the acquisition dates. So let's begin. First, we will open the images in the Product Explorer window. Notice how we have the two images here, and for each image we have two different polarizations. So in fact we have four separate image files. Each image was acquired over latitude 6 degrees south and longitude 56 degrees west. And one image was acquired in 2007 and the other was acquired in 2010. And each image has two polarizations. And here we see the polarizations. HV for horizontal transmit, vertical receive, and HH for horizontal transmit and horizontal receive. Let's have a look at these images. And if we compare the two polarizations from the same date, let's see how they look. We can compare these side by side by selecting Window, Tile Evenly. And in the Navigation tab, if we ensure that these icons are selected to link the viewers and link the zoom and the mouse icon, then we can scroll and zoom simultaneously. Just by inspecting the images, there does not seem to be a great difference between the HH and the HV. If we want to perform some analysis on these images, it helps to have the two polarizations in the same file. That way we can perform ratios, calculate the difference between the images, and do further analysis. To combine the two polarizations into the same image file, we select Raster, Geometric Operations, Collocation. And here we can select the master and the slave image we wish to combine together. So let's begin with the 2007 image. So we select as the master the HV channel and as the slave the HH channel. And here we can call the output image HV and HH. We also should rename the final image bands of this combined product to reflect the master and the slave images. So the master is HV, so here we type in HV, and the slave is HH, so here we type in HH. These are the bands of the output product. So these are the input and these are the output. So we want the output to be named according to the input. And then we select Run. And here we have the combined product. So if we look at the bands of this image, we now see the two polarizations of the same image acquisition date, 2007, in the same image file. Now that these are in the same image file, we can perform calculations on the two bands. For example, if we go to the band mass, we can calculate the ratio. We can create a new band. We can call it HH over HV. I avoid using the / symbol here because the / is one of the characters you cannot use in the naming of new bands. Then if we deselect virtual, then we will write the band to a file. And if we click on edit expression, here we can type out our expression. So HH divided by HV, and OK. And if we click on OK again, then here we have our ratio. And from the ratio we can see more clearly the difference between the HH and the HV. We can go further and create an RGB composite of the HH, HV and the ratio between the two. So if we close all the existing image windows and click on select the name of the file in the Product Explorer window, then go to Window, open RGB image window, then here we can select HH, HV and the ratio as blue. So notice here that all of the deforested areas appear in blue, meaning that the ratio between HH and HV is very high over these deforested areas. So the HH is much stronger than the HV component in these areas, whereas over the forested areas the difference is not so great. We can exploit this characteristic to extract the deforested areas. But first we will do a speckle filtering in order to remove some of the image speckle, because if we zoom in we can notice that there is some image speckle. If we select radar, speckle filtering and single product speckle filter, here we can select a speckle filter to apply. We will choose the Lee filter and we will select a window size of 5 by 5, and we will select as the input bands only the single polarizations and the ratio, and here we will ensure that the output file and directory is as we want it, and we select run. We can now compare the speckle filtered product and the non-speckle filtered product. So if we open the same RGB combination of this speckle filtered product, we can compare them. So here we select HH as red, HV as green, and the ratio is blue. The reason why we select HV as green is because over vegetation you have a lot of volume scattering. And where you have volume scattering, you tend to have a depolarization of the signal. And a depolarization of the signal corresponds to a high return in the cross pole. And given that vegetation tends to be green, it's intuitive to assign the HV channel to green. Now we select OK. And here we have the speckle filtered RGB composite. We can view these side by selecting Window, Tile horizontally, and here we can see the difference between the speckle filtered and non-speckle filtered product. Notice how much of the speckle has been removed in the Lee filtered image. We will now try to mask out the areas that are deforested, and to do that we will apply a threshold on the HV channel. First of all, we need to see what the pixel values are like over the deforested areas for the HV channel. So if we go to the HV image, we double click on it, and if we select pixel info, well, first let's close these other windows, then we select pixel info here, and here we can see the backscatter of the HV channel. Okay, actually these values are in decibel. This image has already been calibrated and converted to decibel prior to the exercise. And here we can see that over the over the deforested areas, we have values of less than 20 dB, and over the forested areas, we have values of around minus 10, 11, 12, 13 dB. So perhaps a suitable threshold in between the deforested areas and the forested areas is around minus 15 dB. So what we will now do, we'll go back to the Product Explorer window, select our input image, and we will go to the bandmass and create a mask including only values which are below minus 15 dB. And we'll call this deforestation mask. We will write this to the file, and here we select Edit Expression. We select the conditional operator, and here we select the HV channel, and we specify a condition that the HV channel has to be below minus 15 dB. And if it is below minus 15 dB, then the mask will have a value of 0. Otherwise, the mask will have a value of 1. And we select OK. And again, we select OK. And here we have our mask. So deforested areas have a value of 0, and the areas covered by forest have a value of 1. We will now perform exactly the same steps on the 2010 image, which I have already done prior to this exercise. So I'll open that here. And we will compare the image from 2010 with the image from 2007 to see the extent of deforestation. To do this, first we need to combine the two images. So we go again to Raster, Geometric Operations, Collocation. And here we input the 2007 image as the master and the 2010 image as the slave. We will write a suitable output file name, so we'll call this 2007 and 2010. And here we will rename the output master and slave to reflect the input. So here we will call this 2007, and we will call the slave 2010. This is just the suffix at the end of the original file name. And we will select Run. And here we have our combined image. We will now try to extract the areas that were deforested in between the two acquisition dates, in between 2007 and 2010, by comparing the two masks. And we'll do that by simply subtracting one mask from the other. So again, we go to Raster, Bandmass. Here we will write the name of the new band, which will be 2007 minus 2010. Again, we'll deselect the virtual in order to write it to a file. Then we click on Edit Expression, and here we type out the difference between the two masks. So we select 2007 minus 2010. And we select OK. The reason why we subtract the 2010 from the 2007 image is because we expect there to be more deforested areas in the 2010 image. We then select OK. And then we select OK again. And here we have the mask including the deforested areas in between 2007 and 2010. having a value of 1 and all other areas having a value of 0. Let's compare this with the two masks. So we have the mask from 2007 and the mask from 2010, and we compare these. So notice that in each mask we have deforested areas, but we also have areas that do not correspond to forest, such as the river. By subtracting one from the other, only the differences are highlighted here in the difference mask. However, we will still have some residual pixels from areas that do not correspond to deforestation, such as the river. Nonetheless, it gives us a good general overview of the areas that may have been deforested. So this was just a very simple exercise on creating a mask of deforested areas in between two SAR image acquisitions. I hope you found it interesting. Thank you for watching.